Section: Introduction. In this section, we discuss the significant advancements in the abilities of large language models, LLMs, to comprehend and produce complex mathematical content. These improvements have come from utilizing a vast amount of public and some private data. However, we are noticing a decline in the availability of high-quality, diverse, and challenging mathematical questions. Finding new questions for evaluation is becoming increasingly difficult, as recent human exams tend to resemble older ones, which may already be included in the training datasets of LLMs. This situation highlights the urgent need for innovative methods to generate new, varied, and challenging questions. We recognize that expert mathematicians and educators have the deep knowledge necessary to create questions that effectively assess a wide range of skills and push the limits of what learners and models can achieve. However, depending solely on human experts is not a scalable solution. While generating synthetic questions using LLMs is a viable option at scale, these questions often lack the required level of difficulty. Some approaches, similar to ours, involve extracting topics and key points from a set of initial problems using models like GPT-4, and then combining these topics to create new questions. However, the generated questions in these cases are primarily intended for fine-tuning models rather than serving as evaluation sets, which results in them not being challenging enough. Moreover, there is limited research focused on ensuring the necessary diversity in the synthetic data generated. Some studies suggest prompting advanced models to create questions within the context of different personas to enhance diversity. They utilize 1 million distinct personas to generate questions, which are then used for fine-tuning models, leading to notable improvements. This contrast between the quality of questions generated by humans and the scalability of those produced by LLMs presents a significant challenge. We also acknowledge the well-known issue of evaluation saturation in LLMs. This saturation is partly due to widespread improvements from better training and more comprehensive datasets, but it is also influenced by evaluation-specific enhancements that optimize model performance on standard evaluations through techniques like supervised fine-tuning on synthetic question-answer pairs. These synthetic pairs can be generated by leading proprietary models when given a few examples or by filtering the model's own responses. Such methods can significantly enhance performance. For instance, just 1 million synthetic examples can boost the performance of Llama 2.7b on the math dataset to levels comparable to GPT-4. It is crucial to differentiate between general improvements and those specific to evaluations. The latter can lead to overfitting to particular evaluations rather than a true understanding of mathematical skills. This concern was highlighted when a new version of the GSM-8K dataset showed performance drops in many models, indicating overfitting to the previous version. Similarly, leading LLMs performed significantly worse on newer versions of the Chinese Gaokao exam compared to older versions, raising important questions about their depth of mathematical understanding. To tackle these challenges, we propose a framework for AI-assisted generation of difficult math questions. Traditional methods of question generation, which heavily rely on human expertise, are becoming unsustainable due to their resource-intensive nature, especially in academic research. Purely synthetic questions produced by LLMs often do not meet the desired standards of complexity and novelty. Our proposed framework aims to combine the strengths of both LLMs and human expertise in a collaborative manner. At first, it may seem counterintuitive to use an AI model to generate and refine novel questions that it cannot solve itself. However, recent research has shown that top LLMs have a strong grasp of mathematical skills, including the ability to identify the skills needed to solve specific questions. This raises the question: can LLMs generate math problems when given a list of skills to be tested? Our initial attempts yielded mixed results. While leading models could create creative math questions based on a list of skills, many of these questions had issues such as being too similar to existing questions, containing errors or nonsensical elements, or being too tedious for human annotators. Additionally, they often confused difficulty with tedious calculations, which actually play to the strengths of machines that can use external tools like calculators or programming languages. Despite these challenges, We found some promising instances where LLMs generated interesting and correct questions that they could not solve due to incomplete or incorrect reasoning. This observation led us to the idea of AI-assisted creation of evaluation datasets. Our process may also be relevant for human teaching, as it starts with extracting core skills from existing math datasets, which serve as the foundation for mathematical questions. Our current focus is on the math dataset, which has been a key resource for LLM evaluation in recent years. By using state-of-the-art LLMs, we generate new, targeted questions that require random pairs of these skills. The involvement of LLMs in creating questions based on these skills introduces a level of creativity and novelty that human efforts alone may not achieve. Our proposed human-in-the-loop approach ensures that the generated questions meet high standards of quality and challenge, benefiting from human oversight and refinement. We begin with a list of mathematical skills extracted from the math dataset and focus on creating questions that involve one skill from the pre-algebra and algebra sections and another skill randomly sampled from different sections of math. Our generation pipeline employs carefully crafted prompts and multi-turn interactions with leading models to significantly enhance the quality of the generated questions and candidate answers. In our AI-assisted process, human experts play a vital role. Using the question-answer pairs generated by LLMs and leveraging API access to leading models, experts identify promising questions, often those that were incorrectly answered by the LLMs but contained many correct ideas. Experts then refine these questions to improve their engagement value and provide high-quality answers. This AI-assisted process not only boosts human productivity but also results in high-quality, novel questions that are distinct from those in existing datasets. We believe that using random pairs of skills is a key driver of improved diversity and difficulty among the generated questions. The math dataset is neatly divided into sub-areas like geometry and number theory. By requiring generated questions to combine skills from two sub-areas, such as linking area and perimeter calculations with prime number knowledge, we encourage out-of-distribution thinking. Our new dataset is significantly more challenging than the original math dataset for all models. For example, if a model has a success rate of 50% on math, its success rate on our new dataset is closer to 25%. This trend suggests that the average question in our new dataset requires a non-trivial application of two distinct underlying skills, which is why we have named it Math Squared. We believe that our methodology could also provide fresh insights into math instruction for both AI and human learners. This concept also relates to how humans might supervise and evaluate AI systems that could potentially outperform humans in many relevant skills. While this is often discussed in terms of alignment and safety, it is relevant here as well. We ask, how can human experts reliably assess LLM's understanding of high school or freshman-level math when these models have already been trained on all available exams and textbooks? Could collaboration between humans and AI lead to more innovative evaluations? Finally, we outline the organization of our paper. We describe our design methodology and generation pipeline for Math Squared, discuss the performance of various open-source and proprietary models on both the math and the new Math Squared dataset of 180 questions, explore the relationship between math and Math Squared scores, and examine the usefulness of Math Squared questions as in-context examples for various LLMs. We also shed light on interesting behaviors and failure modes of leading LLMs that we observed during the question generation process. Section Summary. In this section, we discuss the challenges in generating diverse and difficult mathematical questions due to the saturation of existing evaluation datasets and the limitations of both human and LLM-generated questions. We propose a novel framework that combines human expertise with LLM capabilities to create high-quality, innovative questions by leveraging core mathematical skills, ultimately resulting in a new dataset, Math Squared, that presents greater challenges for models compared to traditional datasets. Section: Pipeline for AI-assisted question generation. In this section, we outline a structured method for creating challenging mathematics questions by leveraging the strengths of large language models, LLMs, alongside human expertise. We provide a high-level overview of our process before diving into the specifics of each step. We start our pipeline with skill extraction, where we identify and catalog various mathematical skills from a dataset. This step helps us build a collection of skills associated with specific questions. Our goal here is to systematically generate and analyze questions that require particular skills, which allows us to create a thorough evaluation framework. Next, we generate questions that combine pairs of different skills to increase their complexity. By utilizing advanced models like GPT-4 and Claude, and including examples of interactions between AI and humans, we improve the model's ability to create intricate questions. This step is designed to produce challenging questions that effectively assess problem-solving skills. The final step involves screening and validating the questions to eliminate any that are invalid or flawed. This careful process includes evaluating and attempting to solve the questions to uncover hidden issues, such as problems with computation or logical inconsistencies. We use advanced techniques like in-context examples and self-consistency checks to ensure the accuracy and quality of the solutions. This step is vital for maintaining the reliability of the generated questions and their answers. Overall, each step in our pipeline is crafted to systematically improve the quality and difficulty of the questions, providing a solid and comprehensive evaluation of mathematical skills. Motivated by these challenges, we adopt a 5-step approach to generate difficult math questions using advanced models. For each round of generation, we randomly select a pair of skills and 3 sample question solution pairs related to each skill from our skill repository, which we draw from the math dataset. Step 1. Skill pair validation. We begin by asking the LLM, GPT-4 or Claude, to validate the skill pair by assessing how similar the two skills are. We provide reference examples in context to enhance the model's understanding. If the model finds the skills too similar, we flag them and exclude them from question generation, as similar skills could lead to simpler questions. Step 2. Question generation. Next, we prompt the LLM to create a question and a brief solution that requires using both skills from the selected pair. We set 2 conditions to ensure high-quality questions. The question should either require an exact answer or indicate that an approximate answer is acceptable, and it should ask for only one final result. We also provide 2 multi-turn conversations between a human and an AI assistant in context. These conversations illustrate how a human gives feedback on AI-generated questions, which the AI then refines. This helps the model anticipate and avoid practical issues, such as insufficient skill involvement or logical inconsistencies. Step 3. Solution attempt. The model then attempts to solve the generated question, taking an adversarial approach to identify flaws like insufficient information, ambiguity, self-contradiction, or excessive computation. If any issues arise, the model stops solving and clearly states the problems. If no issues are found, it completes the solution. During this step, we do not provide the model with the skill names or reference examples to ensure unbiased problem solving. Step 4. Question validation. We present the generated question and its solution to the LLM for validation against a fixed rubric with 7 criteria. 1. The question should ask for only one final answer. 2. There should be only one exact answer unless approximations are explicitly stated. 3. The question must involve both skills sufficiently, with difficulty comparable to or greater than the reference examples. 4. The question should be clear and contain all necessary information. 5. The question should not require overly complex computations. 6. The scenario should be realistic and logically consistent. 7. The question must be grammatically correct and clearly written. The model uses reference examples and validation exemplars to assist in this step. We apply majority voting to enhance robustness. Step 5. Final solution and revalidation. For questions deemed valid, we ask the LLM to resolve the question to obtain a final solution. We provide reference examples in context to improve the model's understanding. We again use majority voting to ensure consistency. If all answers obtained in this step are unique, indicating potential ambiguity, we discard the question. The questions generated through this pipeline undergo further screening by humans. This structured approach not only creates challenging and novel math questions but also ensures their quality through rigorous validation, effectively combining the strengths of AI and human oversight. For detailed examples of prompts used at each step, we refer to the appendix. Section Summary. In this section, we outline a structured pipeline for generating challenging mathematics questions by leveraging large language models, LLMs, and human expertise, which includes 5 key steps: skill extraction, question generation, solution attempts, question validation, and final solution revalidation. Each step is designed to ensure the generated questions are complex, relevant, and free from flaws, ultimately providing a robust evaluation of mathematical skills. Section: Experiments and Findings. In this section, we present our experiments and findings regarding the challenges and quality of the Math Squared dataset, while also examining how different models perform in the task of compositional generalization. To start, we assess a variety of models with different parameter counts on Math Squared and compare their results to those on the original math dataset, which serves as the foundation for skill extraction. Our findings indicate that Math Squared is indeed more difficult than math. Next, we highlight the complexity and quality of the questions in Math Squared by demonstrating that they serve as better in context examples compared to the standard examples typically used. We outline our experimental setup below. For our experimental setup, we follow a specific process to extract skills from the math dataset. This dataset covers 7 main topics, which allows us to pinpoint and extract more detailed skills within each topic and label each question accordingly. After completing the skill extraction, we identify a total of 114 skills. We then eliminate a few basic skills, such as basic arithmetic and arithmetic operations, before using the remaining skills to generate questions through our proposed method. We create and verify 180 challenging questions to form the Math Squared dataset. We also provide a table that details the changes made to the questions during the human verification process. Out of the 180 question solution pairs in Math Squared, 79 were modified by human annotators before being included in the dataset. Among the 41 modified questions, 3 received minor adjustments to enhance clarity. Another 24 modifications were also minor, up to 3 words, but they changed the meaning of the questions and affected the final answers. Additionally, 14 modifications were significant, either making the questions harder, correcting them, or making them more engaging for humans. Regarding the solutions, 62 out of the 180 originally generated solutions were altered to improve clarity or correctness. Overall, 56% of the question-answer pairs in Math Squared remain exactly as they were phrased by the model that created them. We evaluate the generated questions using various language models, both small and large. Specifically, we assess models like MetaMath, Mammoth, Gemma, and the Llama 3 series, as well as PHI-3, DeepSeek Math, and a mixture of experts model called MIXTRAL 8x7b Instruct. We also include evaluations of larger proprietary models such as GPT-4o, GPT-4 Turbo, GEMINI 1.5 Pro, Claude 3.5 Sonnet, and Claude 3 Opus. We compare how these models perform on our generated questions against their performance on the math dataset. For generating responses, we utilize the Mammoth evaluation suite, and we grade the responses using a GPT-4 grader, where GPT-4 Omni checks the correctness of each solution against the true answer. During this process, we set the temperature to 0 and the top probability to 1 for all models. When we analyze performance across the 2 datasets, we observe a surprising trend. Our table shows that all models tested perform significantly worse on Math Squared compared to the original math dataset. If we denote the performance on Math Squared as Y and the performance on math as X, the percentage drop in performance for leading models, such as GPT-4 Omni, GPT-4 Turbo, Gemini 1.5 Pro, Claude 3.5 Sonnet, and Claude 3 Opus, ranges from approximately 13.42% to 35.45%. The Mammoth 7B model, which specializes in math, shows the largest drop at 92.91%. This decline in performance across all models is not entirely unexpected, as the questions in Math Squared combine skills from different subareas of math, making them out of distribution. This leads us to interpret the percentage drop as an indicator of a model's resilience to out-of-distribution scenarios. For instance, the significant drops seen with open-source models like MetaMath and Mammoth are understandable since their training relied on synthetic data generated from seed questions in Math and GSM-8K. The lack of diversity in such synthetic data is known to lead to overfitting to the dataset being imitated. Similarly, we suspect that GPT-4o and Claude Sonnet 3.5 were also trained extensively with synthetic data. Although their performance on math is similar, Sonnet 3.5's poorer performance on Math Squared might suggest lower quality or diversity in its synthetic data. However, we believe that the overall trend among proprietary models of similar size aligns with the out-of-distribution narrative. A simpler explanation emerges when we plot y against x squared. We find a linear relationship suggesting that y is approximately equal to x squared. This indicates that the relative drop in performance of the models can be predicted based solely on their performance on math, without needing to consider their training details. Why might we expect this relationship? A natural explanation is that if there are n skills and S_i represents the success rate of the model in applying the ith skill, then the value of x should reflect the average of these success rates. Furthermore, for a random question that requires applying both the ith and jth skills, the probability of the model answering correctly would be the product of their success rates, S_i times S_j. If questions are created using pairs of skills chosen randomly and independently, then the value of y would be the average of these products, which, due to independence, would be roughly equal to x squared. This reasoning suggests that our process has generated questions that genuinely require the application of two distinct skills, rather than primarily relying on one skill with a minor use of another. The relationship we discovered implies that if we could create questions that combine k skills, we might observe a relationship where y is approximately equal to x raised to the power of k, which would further amplify performance differences between models. Section Summary. In this section, we demonstrate that the Math Squared dataset is significantly more challenging than the original math dataset, as evidenced by the lower performance of various models on Math Squared. Our analysis reveals a predictable relationship between model performance on both datasets, suggesting that Math Squared questions effectively require the application of multiple distinct skills, which may further amplify performance disparities among models. Section. Generated questions are effective in context exemplars for math. In this section, we discuss how the questions we generated serve as effective examples for the math dataset. To evaluate the quality of a question and answer pair related to the math dataset, we can check if using these pairs as examples improves performance on math. We conducted our tests with the understanding that math consists of 7 sections. We selected examples from the relevant section, but our new questions intentionally cross these section boundaries. We developed a method to gather examples from Math Squared based on the skills needed for the current question. However, since Math Squared is not very large, it only includes 97 out of the 114 skills we identified. We also looked at the distribution of skills in the dataset. To ensure our evaluation was fair, we filtered the math test set to remove any examples that required skills not found in the generated dataset, which led to the removal of 809 test examples. During our evaluation of the filtered math test set, for each question labeled with a specific skill, we retrieved examples from Math Squared that matched that skill. We used 4 examples for each question, which we refer to as a 4-shot chain of thought. If a skill had fewer than 4 examples in Math Squared, we ran 2 experiments. A. In our proposed 4-shot chain of thought, if a skill had n examples in Math Squared where n is less than 4, we used n examples instead of 4. B. In our proposed skill-based 4-shot chain of thought, if a skill had n examples in math squared where n is less than 4, we supplemented the remaining examples from the math training set. We determined the relevant examples in the math training set using a specific methodology. We compared the performance of our models using these targeted prompting strategies against two baseline methods. C. Mammoth 4-shot chain of thought, where the 4 examples come from the Mammoth evaluation suite, and D. Skill-based 4-shot chain of thought, where examples are selected from the math training set based on the skill required by the question, as identified by GPT-4. The results of this comparison are presented in a table. Our two prompting strategies that utilized questions from Math Squared as examples clearly outperformed the two baseline methods. We conclude that the questions from Math Squared, due to their complexity and relevance to the skills, are effective examples. We believe that performance improvements would be even greater with larger datasets generated using our approach, which would lessen the need for external examples. Next, we reflect on the question generation process. The pipeline we developed involved refining prompts and design choices through an iterative process, assessing how these changes affected the quality of the final questions and solutions. We found that including attempted solutions and validating questions significantly improved the pipeline's effectiveness. Despite the sophistication of our methods, we still noticed instances where models did not follow the instructions correctly. This section highlights key failure points in the pipeline that human raters should be aware of. We also explore some interesting behaviors of the models, where they successfully generated creative questions. Regarding creative questions, we observed that the models often produced intriguing and imaginative questions, although they frequently failed to provide correct solutions. In these cases, the incorrect solutions usually contained enough correct ideas for a human to complete them quickly. Human annotators were responsible for verifying the validity of the questions and the correctness of the solutions. They were instructed to be mindful of the failure modes we discussed earlier. Their tasks included ensuring that the generated questions utilized the intended math skills and improving the questions in terms of readability, quality, and difficulty whenever possible. They were encouraged to suggest modifications that would make the problems more challenging for automated tools while allowing for easier or more elegant solutions for humans. We provide several examples to illustrate this process. For instance, one original question asked for the smallest positive integer k such that k cubed minus k is divisible by both 9 and 10, and the sum of the digits of k is a prime number. Our human team had not encountered such questions before. It required recognizing that k cubed minus k is always divisible by 2 and 3, meaning k must be such that k times k minus 1 times k plus 1 divided by 6 is divisible by 15. Additionally, ensuring that the sum of the digits of k is a prime number is quite challenging, even for advanced models. Another original question involved a collection of beads of different colors arranged in an infinite series, where the number of beads in each section followed a pattern of powers of 2. The human rater modified this question to change the sequence size from 20 to 6 beads, maintaining the essential difficulty while making it more elegant for humans. All tested models struggled with the modified question. In another example, we started with a question about a container that initially held 500 milliliters of water, with a scientist adding a quarter of the current amount every minute. The modified question simplified the scenario, asking for the smallest positive integer n such that the number of liters of water in the container never falls within a specific range. This adjustment made calculations easier for humans while presenting a different challenge for the models. Lastly, we had a question about a recursively defined sequence. The original question asked for the product of the first 5 terms, while the modified version required finding the logarithm of a specific term in the sequence. The original question was straightforward for models, but the modified one required a deeper understanding of patterns. These examples highlight the crucial role of human oversight in refining and enhancing the questions generated by models, ensuring they are challenging, creative, and suitable for advanced mathematical problem solving. Section Summary. In this section, we demonstrate that generated questions from the Math Squared dataset serve as effective in-context exemplars, significantly improving performance on the math test set compared to traditional baselines. We also highlight the importance of human raters in refining these questions, ensuring they are challenging and creatively structured, while addressing common failure modes in the model's outputs. Section: Failure Modes. In this section, we identify several failure modes that our models frequently encounter, despite the sophistication of our pipeline. First, we notice that there is often insufficient involvement of skills. This means that the models sometimes generate questions that completely overlook one of the necessary skills or only require a very basic application of one or both skills. For instance, a geometry question might not adequately incorporate the concepts of ratio and proportion. Second, we find that some questions lack essential information. This can make them incomplete or ambiguous, such as a trigonometry question that fails to include necessary angles or distances. Third, we encounter unsolvable or computationally difficult questions. Some generated questions are either impossible to solve or demand excessive calculations that are impractical for assessing reasoning abilities. Fourth, we observe that models occasionally produce nonsensical questions. These can be logically inconsistent, confusing, or ambiguous, like a probability problem with unclear parameters or an impossible geometry scenario. Fifth, we sometimes see deceitful solutions. In these cases, models may create answers for nonsensical or unsolvable questions, presenting incorrect logic as if it were reasonable. Lastly, we experience challenges with finding a needle in the haystack. Long and complex validation prompts can lead models to confuse or overlook the specified skills, resulting in incorrect evaluations. For more detailed discussions and examples of questions in these various categories, we refer to the appendix.